Soledad.
Soledad. Okay.
Yeah.
Thank you.
Hi, I'm Yuxing. I'm from Johns Hopkins, and I'm advised by Soledad. So today, I'd like to share some thoughts about size generalization. So specifically, models like DeepSet, GNNs, and transformers, they are designed to process inputs of any arbitrary sizes. So the question I like to answer is that for what kind of data and task can these existing models be trained on smaller sizes and generalized effectively to larger ones? So my answer to this question involves two key points. The first is a task model alignment, and the second is that the training and test distributions should be similar relative to the model's inductive bias. So to illustrate what I mean exactly here, let me start from a simple example, the DeepSet. And it is also commonly used as a global readout operation in GNNs for graph-level tasks. So the input is a multi-set of n vectors in RD, and each one of them is processed by the same MLP phi. The outputs of phi are then processed by permutation invariant aggregation, followed by another MLP row. So the original DeepSet uses some aggregation, but it's also reasonable to use a mean aggregation, which gives you a normalized DeepSet, or a max aggregation, which gives you the point net. So notice that since the model is designed to take multisets of any size, so the domain of this, the function that it parameterizes is really the union space of Rn by D over all possible set size n. So to analyze size generalization, let's assume some target function also defined on this space, and a training distribution that's supported on small set sizes, and test distribution supported on large sizes.
What is phi here?
Phi is an MLP.
An MLP.
Yeah, and rho is also an MLP. Okay, so so for the model to actually generalize to large unbounded sizes, the first, it's quite natural that expressivity is a necessary condition. So we require the existence of a learned model that can well approximate the target function on the entire union space, and that's a notion of uniform expressivity. Unfortunately for us, for these three simple models, it's reasonably well understood what kind of target functions can be approximated uniformly. So for these models, we have universal approximation theorems of the following form. The model can approximate a function f star if and only if f star is uniformly continuous with respect to some pseudometric on the union space. So notice that for this continuity of such a function to be defined, it requires a notion of distance metric on the domain. And there are many reasonable ways to do it. But so it turns out that each one of these three models corresponding to a different notion of pseudometric. So the normalized DeepSet, it parameterizes continuous function with respect to a Weierstrass distance, where for two multisets of different sizes, we measure the distance between them by taking the Weierstrass distance between their corresponding empirical distributions. The thing to notice here is that under this distance, multisets of different sizes can be considered equivalent. For example, like if we just duplicate each entry multiple times, the two sets are considered equivalent under this distance. And for point net, it parameterizes a continuous function with respect to a different distance, a host of distance. But the similar things happen here. Like it identifies some equivalences between objects of different sizes, like this example here. And for DeepSet, the result is not fully proven yet, but we hypothesize that it's corresponding to L1 distance. And in this case, it's slightly different. The multisets of different sizes are usually farther apart under this distance. And on the one hand, it's more expressive in the sense of like distinguishing different sets. But on the other hand, it's exactly this property that make it has less desirable size generalization behavior. And like it will be illustrated later why that's the case. So we have three models corresponding to parameterizing continuous functions with respect to three different pseudometrics. So it is exactly in this pseudometric that characterize the hidden inductive bias of these models. so essentially, like each one of them encode in itself a different notion of equivalences or proximity of objects of different sizes. And this property affects how and when these models generalize in size. So the claim I'd like to make is that if we have a universal approximation theorem of this form that says a model like parameterize a function that's continuous with respect to some pseudometric. And then this statement gives us a lot of useful insights on size generalization. Why is that the case? So first, if this target function is not uniformly continuous with respect to the pseudometric, then this statement tells us the model cannot approximate this target function uniformly, so it cannot size generalize well. The example from the deep set case, like two simple examples. The first one, like let's consider a target function that's a continuous function of mean and higher order moments. Such a function is continuous with respect to Wasserstein distance, but it's discontinuous with respect to either Hausdorff or L1. So PointNet and deep set probably cannot size generalize this on such task. But if you use normalized deep set, maybe it can work. And the second example is the diameter of the set. And in this case, it's continuous with respect to Hausdorff distance. So only the PointNet can possibly work for this target. So this highlights the importance of a task model alignment. And we further hypothesized that the degree of such alignment maybe affects the degree of the size generalization capability. And we do have some experiments about it in our paper, but it's in general quite hard to formalize how to formally measure the degree of the alignment. And I think it's an interesting future direction. So on the other hand, let's consider the case where we do have perfect task model alignment. And in this case, the training fundamentally happens on this union space with this pseudometric. So size generalization happens if the training distribution and test distribution are similar with respect to this pseudometric. And notice that, and recall that previously we've said that under Manning pseudometric, it defines a lot of equivalences between objects of different sizes. So this makes it very possible here for the training distribution and test distributions to be supported on very different sizes, but they can be similar under this pseudometric. And the simple example here is for normalized deep set, which corresponding to the Wasserstein distance. If we consider a distribution on multisets of size n, where each entry of this multiset is sampled IID from the same distribution, then for different size n, these distributions are very similar together. So size generalization can happen on such distributions. And on the other hand, if the training and test distributions are not similar, are far apart under this pseudometric, then because of this universal approximation theorem, the model can fit the training data quite well, but it can has the freedom to have very arbitrary behavior on the test region, while the training data is still have small loss. So size generalization is very unlikely under this case. And this also points to the situation where if this is for this pseudometric, any two objects of different sizes are far apart, then the model basically cannot size generalize on most of the tasks. And for example, this I think is what's happened to deep sets to some extent.
I wonder what the task complexity here, because in some cases, because the task may also impact the design of the pseudometrics itself. So what is the task complexity here?
So this is a case where I assume there is perfect task model alignment, which I assume this target function is uniformly continuous with respect to this pseudometric.
I mean what to evaluate, because you have the objective such as the task, for example, counting or something. What is the task complexity here instead of the theoretical result part?
What do you mean by?
The task for evaluate, maybe we can talk after the meeting.
Yeah, let's chat afterwards. So the conclusion I want to make is that if we have such universal approximation theorem of this form, then size generalization happens if and only if we have the two conditions. The first is the task model alignment, and the second is training and data distributions are similar with respect to this pseudometric. And I think this is something that we can both analyze empirically and theoretically. And so so this really motivates us to ask, like, do we have the same form of universal approximation theorems for GNNs? And yes, we do have these results, many from the audience. And like for the sum aggregation, so these results, I think, immediately tell us many things about size generalization. For example, it tells us that the size generalization of message parsing neural networks are fundamentally controlled by the aggregation functions. And if we use the sum aggregation, I think similar things happens as compared to the deep set, that this pseudometric usually identifies the any two graph of different sizes to be far away. So size generalization cannot happen mostly, except if we restrict it to sparse, bounded degree graphs. And for this normalized sum aggregation, where we divide it by the size of the graph, then this is really the regime where most of the GNN transferability result is about. Because in this case, any two graphs that's corresponding to the same step graphon will have the same output, and they are identified as equivalent under this pseudometric. So, and I think an interesting question here is what happened for max aggregation? Do we have a corresponding pseudometric there? I think it's a nice question for further studies, and also it's interesting to understand what kind of target functions are continuous with respect to these different pseudometrics. And I think that will allow us to have a better understanding about size generalizations of GNNs. So yeah, that's all I have. And some of these ideas are explored in more details in our new preprint with Eitan, Matteo, and Soledad. And if you are interested, check it out. Okay, thank you.
Oh, wait, Hannah.
Did you test, I mean, obviously the theorems are proven, but did you do any empirical tests to see, in the cases where it should be able to size generalize, if you actually find size generalization?
Yes, we have some empirical results in our paper.
And generally, do they mostly align, or with what you expect, or?
Yes, so they are all simulated data. They are not, so just to control that the task function are continuous. So yeah, and they work quite well, they are as expected. Cool. Thank you.
Thanks again.
Trying a faster computer today.
Hannah is back.
Nice.
Okay. Our next talk is from Hannah, who you'll remember from yesterday.
Oh, good. Okay. Awesome. Yeah, well, thank you. Let me just check the time. Okay, 4:19. Thank you for having me back for the lightning talk. And I thought it would be fun to talk about, so I guess this is kind of a disclaimer, stuff I'm thinking about right now with collaborators. It's sort of, there's some stuff that I think is settled and some stuff that I'm very interested to hear people's thoughts on. So this talk is going to be about distributional symmetry breaking in the context of equivariance. So hopefully you remember the boot camp talks from yesterday, but I'll try and keep things pretty high level if not. But first, we're going to talk about bird watching for a second. And so this example credit goes to my collaborator, Robin. But imagine you're trying to distinguish between different species of birds. And you, in particular, want to distinguish between the brown creeper, who it turns out walks up trees, and the nuthatch, who walks down trees. So these are two different birds. This is a perfectly well-defined problem. And you could take this bird off the tree and hold it at any orientation you want, and they would still be two completely different birds. So the underlying classification function here is invariant. But there's actually information contained in the pose, right? Because if you have a picture of a bird and you're trying to figure out which one of these two it is and it's walking up the tree, it's much more likely to be the brown creeper than the nuthatch because they have these preferred orientations in the wild. So an equivariant model, although the underlying function truly is equivariant, or in particular invariant, it actually can't harness any of this pose information. So, because, for example, you're getting rid of it by saying I'm doing everything invariantly. And I can maybe put this into more familiar machine learning benchmark data set world with 6s and 9s, right? So these two digits look very different. You can easily distinguish them. But if you apply a 180-degree rotation, suddenly they look very similar to each other, right? And so digits actually, much like the birds, have a preferred orientation, which does convey useful information, even though actually technically, and you can test this with the classification network, they are like technically distinguishable. Like this is technically an invariant function. The way people tend to write like 6s and 9s are slightly different. But nonetheless, it would still be very helpful to be able to know what the naturally occurring orientation of this data was. And we can sort of visualize this as orbits. So an orbit just refers to all possible rotations of your input data. And in naturally occurring data, the probability distribution is super non-uniform over these orbits. So 6s, people write in a specific orientation, and 9s, people also write in a preferred orientation. But now imagine I told you were going to apply data augmentation to this problem. And so that means like before I process my data, I apply random augmentation to it. I'm essentially destroying this information entirely. So now the probability distribution is totally uniform over orbits. As far as I can tell after I've augmented, they're all equally likely to be in all orientations. And so what have I just described to you? So like what's happening here? The underlying function, and I want to emphasize this, is entirely rotation invariant. Like the labels we are trying to learn, they truly are rotation invariant. But the data distribution is not uniform over orbits. Like x and g of x are not equally likely to occur. So the different species of birds or digits have preferred orientations. And so theoretically, the best possible invariant model is going to get 100% accuracy, right? Because the ground truth function really is invariant, and it can still tell the difference between the birds, but intuitively, you're forcing it to use features that are potentially harder than the orientation. So like in the bird example, you have to look very specifically at the color of the feathers and low-level details, as opposed to potentially using an easier non-invariant feature that also happens to work pretty well at this prediction task. And so in fact, although I've given you these sort of two random examples, lots of data has preferred orientations, right? Like obviously the smug looks wrong to everyone because they tend to appear in this particular orientation. In addition, on the leftmost side, that's an example from the Open Catalyst data set where you have catalysts and slabs, and like the crystal part is always sort of on the XY plane. Also faces, right, tend to appear in certain orientations. And I want to talk about two different cases. So we have superficial cases, right? So in the cases of something like this crystal data set, it's been sort of user-defined. The fact someone decided to put the crystal on the XY plane, that wasn't like a naturally occurring process. Like we had full control over that, right? In other cases, like in the MNIST data set, there was actually some fundamental process in the data generation that gave rise to this asymmetry in the orbit, in the distribution over the orbits. And moreover, we're sort of assuming that this is replicable, like this is a real trend most of the time. And so why do we care about this? Why have I chosen this as the topic for my lightning talk and some recent research? Well, first, just in general, like understanding your data is quite important from a lot of perspectives. But more specifically, let me paint like two different pictures for you. So one is, let's say you only care about generalizing in distribution. Like your data set is your data set. There's not going to be any change to it. If you use an invariant method, because your underlying function like genuinely is invariant, you might be throwing away useful information without realizing it. Because in particular, you're throwing away the information about what was the pose of the input object. Now, perhaps you care about generalizing out of distribution, right? I would argue that in the equivariance world, this is very often the case, where you say, hey, I want to generalize to new orientations. I don't just care about my validation set. Well, it's still good for you to figure out what's happening here and to figure out that you have asymmetry, because if you use a non-invariant method, you might be led astray by over-optimistic performance on a validation set that actually is very constrained in the poses that appear. And so the goal here, first, is to quantify the extent to which benchmark point cloud data sets are distributed evenly over rotations. And so there is some prior work sort of setting up this hypothesis test framework for doing this in the abstract based on kernels. We're going to sort of extend this a little bit to the neural network world and then actually like try this on the data sets that people are using in the experiment section of all their equivariance papers. And then empirically, what I'm really interested in is what are the implications of this phenomenon for learning? Like should ultimately, you have a practitioner, they want to know like, should I augment or not? Like what can you tell them? And I just want to note this is slightly different from the symmetry discovery literature, although it is related, because again here we're assuming that we know the group that the function really is invariant to, and it's a problem of distributional asymmetry. So let's start with this quantification. So how can you measure how asymmetric your data set is over poses? And I'll refer to this asymmetry sometimes as canonicalization. It may not be exactly canonicalization, but like in the cases of sixes, right, it's practically canonicalized. Like they usually occur in a very, very similar orientation, not uniformly overall. So here's what I propose doing and when I'll tell you the results about. So you start with this data set. This is the data set you want to understand better. Let's split it into two halves randomly. On one half, we're not going to change anything. And on the other half, we're going to randomly augment it, each element independently. And now we're going to turn this into a binary classification problem. So the original data set is class label 0, and the rotated data set is class label 1. And we're going to ask a small neural network to distinguish between these two. So this is a classifier distance between two distributions, just kind of convenient for working with different data types. And we're going to ask, like, OK, what is the test accuracy of the classifier? How well can I distinguish between my actual data set and if I were to have augmented it? And so if you get 50% accuracy, this indicates that probably all the rotations were equally likely in the data set, right? Because this was actually an impossible classification task, because your two distributions would have been functionally the same. On the other hand, if you get 100% accuracy, like I can always tell you if this example was randomly rotated or not, that means it had to have had some sort of preferred pose or a small number of preferred poses in your original data set. So right off the bat, this gives us like a number, a spectrum between 50 and 100% accuracy that tells you like exactly how far is your data set from being totally uniformly distributed over orbits. And I should mention also that in the theory of equivariant learning, a lot of the classical results that say like you get an improvement from doing equivariant learning tend to assume you have uniformity over the orbits. And we actually have some theory in our work that says like when you break this assumption, this may not be the case. So some of those results break when you break this uniformity assumption. So OK, so I just described this metric to you. What do we actually find in practice? It turns out that, and we didn't know this coming into it at all. I was kind of surprised. Maybe if you've worked with these data sets a lot, you're not. It turns out that essentially all of these point cloud data sets, at least the ones we could find, are super non-uniform over orientations. So for example, if you look at the QM9 data set, this is like a small molecule data set. It's quite common in benchmarks for all sorts of point cloud learning tasks, as well as sort of in the drug discovery community for benchmarking your methods. This is a visualization of literally what the molecules look like, sort of right from the data set. And this is like very visually obvious even that like clearly these long backbones are being aligned vertically. They're not just at random orientations. Same for ModelNet, right? This is a data set of furniture, so you sample points from different CAD models of items of furniture. Once again, this classifier can get 92% test accuracy, which kind of makes sense that like a chair usually has a preferred orientation in reality. So this is like quite strong overall, right? These are all quite high numbers, and we did sanity check this by like we checked, you apply random rotation and then apply the test, like it does get 50%. You randomly rotate some of the data set, like we ran these sort of sanity checks on the metric as well. Turns out though that these benchmarks are all super canonicalized. So what does this mean for learning? And I think this is where the maybe more interesting question or opportunity, both in theory and in practice, arises. So we look at these data tasks, which all have their own sort of standard labeling tasks, and we look at them in 4 settings. So you can do augmentation on the training set or not. And then you can ask if you care about out-of-distribution generalization, which is test time augmentation, or if you just care about the sort of existing test set, which has the same distributional asymmetry to it. So these 3 settings are often tested in prior work on equivariance, but people usually don't test the setting, as far as I know, where you augment and then you don't care that you augment to try and do better on your original test data set. And when you do train time or augmentation, as I said, the preferred orientation of the inputs is lost versus retained when you don't do train time augmentation. And once again, the diagonal here is in distribution, whereas you have a distribution shift when you're not matching your train and your test augmentation. And you kind of perhaps intuitively would expect that when you don't have distribution shift, like this is supposed to be the best case performance. So first we try ModelNet 40, and basically everything looks kind of like you would expect. The best performing cases are when you don't have distribution shift. So if you want to do best on ModelNet 40's validation set, then you shouldn't use augmentations. Another interesting case here, there's just one paper that I tested this with. I'd like to do it with more. There's this paper that fine-tunes LLMs to generate crystals but it represents those crystals as text. And so there's some string encoding that happens of this crystal data set before it's fed into a llama model. And we can then look at this text data set and ask, well, is this canonicalized with respect to permutations, or are all of the atoms in some like totally arbitrary order? And once again, it's super ordered. And you can even like look at it and see that the atoms like are all like sort of the same atom always appears next to each other. You're not looking at all random orderings, even though it fundamentally is a set that you're working with. And the reason I think this one is interesting is that the paper actually found independently that permutation augmentations hurt performance here. So here you have a case where the data set is super canonicalized, but doing augmentations is a bad idea. And so this was actually part of the inspiration for this study, but I think this is kind of interesting because they weren't thinking about the canonicalization of their data set at all. They were just kind of like, oh, we tried permutation augmentations, they didn't work. And I think this is one way of understanding that. But one mystery that I want to present to you that I don't really have a great answer for, although I have some hypothesis for, is that on this data set of molecules, we found something kind of surprising, which is that actually augmenting on the train set is, for some properties that people care about, is actually helpful, even if you only care about generalizing to these molecules which are already canonicalized. So to me, this is super unintuitive because you're sort of teaching your model about rotations, but you actually don't care about global rotations in the test set. And one thing that we tried here as like a hypothesis, or okay, I'll just reiterate the question, why does training on the augmented data set improve performance on this unaugmented test set? And this is kind of a more general ML question, I think, of like, why does pre-training on data set A help you on data set B? And that feels like a very hard question in general, but these are very like closely related data sets to each other. So I would hope that like perhaps it's possible to understand this phenomenon and like why it happens for some data sets and not others. And one possible explanation that I have, but you can see if you're convinced by it, I don't know yet if I'm entirely convinced by it, is thinking about locality. And so let me explain sort of what we tried and what the intention was. So you start with this QM9 data set, and I'm going to actually turn it into a new data set, right? So we know that this data set has a lot of distributional symmetry breaking. Like not all orientations actually appear with equal likelihood. So what I'm going to do is for each molecule, I'm going to randomly choose a neighborhood of the molecule, and I'm going to put together all those neighborhoods into a brand new data set. This is what I call like the local QM9 data set. So this sort of captures like what are the local graph motifs, 3D graph motifs that show up in molecules. And obviously, as you would expect, like there's a lot of repeated ones as well. And so now we can actually ask, well, how much distributional symmetry breaking is there on this data set of motifs? And when we run the same exact classification experiment, we get far lower test accuracy, so 67% compared to like closer to 99%, which indicates that local motifs in molecules are much more evenly distributed over poses, even though there is some sort of global canonicalization that happens. And so one sort of weak hypothesis that I have, I don't know if this is certainly not causal evidence by any means, is that perhaps local equivariance is captured by augmentation. So you're sort of teaching the model that any of these motifs in any rotation has some similar features in a way that like canonicalizing wouldn't. But I think this is maybe, I'd be interested to hear if anyone has thoughts on this, if you're convinced or not. I think to me it's still a mystery why augmentation works so well for molecule data sets, even when they are so canonicalized already. And so, yes, okay. Time-wise, I will just summarize now. So benchmark point cloud data sets and at least one sort of language model data set for science, possibly more, are super non-uniform over orientations, and in the case of the language model data set, permutations. This definitely has some type of implications for whether or not you should use equivariant methods, although there's still kind of a mystery about these molecule data sets, like why rotation augmentation is so helpful for them. But I think, to me, this is sort of a little bit contrary with how I used to think about equivariant learning, and in particular, all of these very nice theoretical results that we're saying, like you should always use an equivariant model as long as your labeling function is equivariant or invariant. And as I mentioned, we have like theory about when this breaks, when this assumption on the distribution breaks. And finally, one thing I'm very interested in, and I don't have a good answer for, is this like ongoing direction, which is that I was sort of telling you about how to quantify if your data set was distributionally asymmetric at all. But actually, what's really interesting is understanding not just is there some random like asymmetry, but is that asymmetry useful for the task? So like, is it like the MNIST 6s and 9s where the way that it's oriented is actually like directly predictive of the label? Or is it just sort of like a nuisance variable and like you don't necessarily need to worry about it as a spurious correlation? And I think having a metric that can actually capture the relationship between the canonicalization and the task would be, I personally would be very interested in. So, if you have ideas, certainly happy to hear them. But yes, I will just say thanks to my collaborators on this from Northeastern, MIT, and UCL. And I will leave it on this slide. Thanks.
So in your experiments, you used augmentation, but you didn't use an invariant method. Do you think that they're equivalent, or?
Okay, this is a good question. We did actually use some invariant models in the experiments. The trouble is that it's hard to have a apples to apples comparison between a generic model and an equivariant model because the architectures can, in general, look quite different. And so we viewed sort of augmentation and group averaging as the best apples to apples approach. Generally, what I would expect is that if there is useful information in the orientation of an object, that an equivariant method also cannot pick up on it. But if augmentation works well, then an equivariant method that is with a reasonable architecture should also, I think, be pretty helpful. So we've done a couple of experiments on this, and generally this seems to be the case that the performance is correlated. The equivariant models we used were a bit better than augmentation, but they still don't capture the information of the pose sort of by definition. And the theory also covers equivariant models as well. Yeah.
Regarding the sort of the data set, do you mostly focus on these point cloud data set? Have you also looked at maybe just generic graphs? Or is it here the focus is really this Euclidean symmetry?
So that's a good question. We focus on point cloud data sets, but I think the question is super interesting for basically any group equivariance that you may have. So that I guess we did look at permutations for this language data set where you're permuting atoms. We haven't looked at any non-geometric graphs. And I think this type of thing is very interesting for permutations in the context of language models, just because they are such a large group that if you if your data is already sorted or canonicalized in some way, that might be some key to performance. But yeah, not combinatorial graphs could be cool.
Let's say, for example, in the example of the birds, that the bark of the tree, looks very differently when the bark is facing upward versus downward. Then, you're not really capturing the right kind of equivariance by rotating the image after it's taken, because what really matters is the orientation of the bird relative to the bark. So is there any hope for capturing equivariances of this sort?
So sorry, you mean that if, so you're saying okay, suppose the bark can distinguish between the two orientations, then if I give you an upside down picture of one of the birds, you know that it's upside down? Yeah, that's a good point. That's probably true. I would argue that the underlying function is still invariant, right? You just say, oh, someone flipped their camera around, but the bird itself still has the right features. I think in that case, you might be less worried about, or I guess the canonicalization is a bit more subtle, but the underlying phenomenon I think is the same. I'd have to think a little bit more about what this means for how you think about the canonicalization of the two. But yeah, it's kind of telling you if I knew the orientation, if I knew the camera angle, right, this would kind of change the problem as well. It's there's some exterior information that hasn't been given to you about how the data set was generated, and that's kind of what we're trying to back out in a sense for these molecule data sets.
We should be quick. But
So about the molecule, the QM9, I think it's called. In that case, your experiment was testing, in a sense, if the local pieces have a higher homogeneity of their distribution.
Yeah.
But another something you say as a hypothesis would require another kind of, maybe there is another kind of test that you can do in order to say, if I do augmentation, does the learned function have higher locality? So I don't know how to test that, but it's maybe you know.
Yeah, that's a good idea. We haven't tried that. I didn't think about that. Thanks.
thanks.
Thank you.
Why don't I hold this? this for you.
So my name is Filip Kučerák. I'm a first-year PhD student of Dan Kral, co-supervised by Matija Bucic. I'm currently at the Max Planck Institute in Leipzig, Germany, and I mainly focus on probabilistic and extremal combinatorics. Yeah, so I came here to learn about learning, and so the topic I want to present to you today is a very foundational question about extremal questions about motif densities in large networks. So I'm going to start by a definition of a density. So given some graph f and g, on the slide I have the definition by k-graph. So k-graph for me is just k-uniform hypergraph. So graphs where instead of edges being pairs, I consider sets of size k. Then we say that pattern density of f and g, or motif density, is simply the probability that if I randomly choose induced subgraph of g that is of size f, it will be isomorphic to f. In my regime, you should think f is very small fixed graph, so for example edge, triangle, C4, and g is some very large graph or network. All of the theory I'm going to discuss can be even formulated using the language of graphons, which you've seen yesterday, or hypergraphons, but today I want to keep everything finite. So sort of a very obvious question here is, okay, so if we fix some network G, what relationships are there between the pattern densities between different f's? So for example, it is obvious that if my density of a triangle is 0, the density of the edge cannot be 1. Right? If I have all the edges, I better not have any. I better have a triangle. And so a very natural extremal question arises. Okay, what is the maximum number of edges I can have while being still triangle free? Yeah. And as I said, we usually care about networks with order going to infinity, and so we care about the limit of these maximal densities. We call this the Turan density of the motif. So let me keep the definition and state the classic. So there is a theorem which is by now over 100 years old, and it says that if you want to produce a very large dense graph that doesn't contain a triangle, there is nothing better you can do than to take the complete balanced bipartite graph. And this gives you roughly half the edges. So this question asks about forbidding triangle. We can forbid different graph f and ask about the maximum density, and this is known. And this is due to a very classical result by Erdős and Stone. And for any motif f you give me, the answer essentially comes down to its chromatic number. But the punchline here is that if we start looking at hypergraphs, or even free uniform hypergraphs, we know very little, very, very little. For example, if I consider the complete graph on 4 vertices, so this can be visualized as tetrahedron because it's 4 vertices where every triplet is an edge, we don't know what its maximum density is. Yeah? We think it should be 5/9, and on the figure I have the conjectured extremal construction, but as of now there is no proof. Maybe to motivate the audience why the question is interesting to resolve. Well, because resolving the question earns you $500 from Erdős. Yeah, this is one of his famous, questions with prize money. Yeah, so there is this very huge difficulty jump when going from graphs to hypergraphs, and this warrants studying the question even if we look at even if we optimize only over hypergraphs with additional structural constraints. And mainly what I want to look at is hypergraphs which are uniformly dense. So if we look at the construction which achieves the biggest density and avoids triangle, this bipartite graph, it is clear that although the graph is globally dense, it has roughly half the edges, there are these two large parts that are completely empty, right? There are simply no edges. And what we can ask in the land of hypergraphs is, what if we require it that on every large induced subgraph, we see the edge density, right? So the edge density is sort of uniformly spread. Interestingly, maybe in graphs, this question will become completely trivial. Once you require the density to be uniformly spread, the maximum density of every motif will be 0. This is the area sometimes called the uniform Turan density, and this was popularized by Erdős and Sjös in 80s. But this area was for 30 years completely dormant. No new results were known. But in the last 15 years, because of some techniques coming from hypergraph regularity lemma, which was independently established by Gowers and Koha, Yakava, Nagel, Rödl, Schacht, and Skokan, this lemma is generalization of the very famous Semeredis regularity lemma, allowed us to get some results. But even still, the area remained very difficult. Proving this uniform Turan density was very hard. And up until basically like 2 years ago, we only knew two densities to be achievable. Only finite number. The densities were 0, 1/27, 4/27 was, for example, the Turan density of tight cycles. 1/4 was the Turan density of this tetrahedron if you remove one of the triples. And that was it. That was the complete list. And it was hard enough to establish these densities that even a result which only says there exists a graph whose uniform Turan density was 8/27 is now modulo some minor revisions accepted to CPC. But by now, due to recent developments created by Lamaison, this new characterization of this notion of uniform Turan density, which I did not define formally, but I hope at least the intuition was clear. We know a lot more. For example, he proved he resolved the uniform Turan density of all stars. And maybe a little funny thing here is that this was the first time somebody established infinitely many of these densities at once. Yes, before you would really do density by density. Yeah, that's everything from my side. Thank you very much for your attention.
Do you think machine learning can somehow help to prove some of the theories?
Yeah, so one of the reasons why I'm very interested in graph learning, because a lot of the tasks we have are sort of combinatorial optimization tasks. And at some point we even tried using these machine learning techniques to achieve, because for example, to get these constructions, if I just tell you I will forbid you from containing some fixed pattern F, you have no clue what this extremal thing should be. And so it is a generally very hard task to get them. And there are some methods, usually coming from optimization theory, but maybe one could use ML here.
And the optimization algorithms that worked, that helped, or?
I mean, these are going to be very ad hoc. Like you are just going to try some very local greedy search or something.
Nice.
So nothing. I mean, there are for getting these constructions, they are going to be ad hoc. For getting upper bounds, whatever it means in this setting, there is a method called flag algebra, which is this computer-assisted optimization technique. But I don't want. Yeah, it will be hard to discuss.
so I was given this. For
Yeah, that's fine. Either one is fine.
Okay.
Why don't I just give you this one? It's easier.
Oh yeah, this is already.
Pocket. Your waist.
Is it asking? Try it again.
Yeah, just go to choose. Yeah.
Last but definitely not least, Tien?
Yes.
Yeah, thanks.
Okay. Okay. Thanks. Thank you very much, everyone. Hope you have been enjoying the workshop. So a bit about me. I'm Stephanie Jagielka student at MIT. I'm defending my thesis next week. So I'm very borderline between graduate students and not graduate students. Hopefully. Yes.
Could go either way, you're saying.
Yeah. Okay, but yes, about my research. So a bit of introductions, I guess, about what I'm interested in and what I see as the light at the end of the tunnel is my research focus on exploring implicit simplicities of graphs for analysis for machine learning on graphs, and we use this wonderful and very versatile object called graphs. That is, extremely useful and can be used to model almost everything. But it has lots of implicit simplicity that makes the analysis or the computations a bit simpler. For example, you have regularity lemmas in the styles of similarities, for example, and that gives you things like compactness of the space of graphs, for example, graph forms with the cut metrics. And this compactness comes in hand when you want to prove things like generalization bounds, covering numbers. It all comes from this kind of random structures from randomness results. Or you can have things like if you don't want to go to Wowzer's number of nodes, you can still have other kind of simplicities. Like if you have a power law degree distributions for community graphs or examples, you have like rich triangles, for example, in your graphs. Or because, for example, the range of the graph form shift operator is finite, you can talk about the some spectral domains analysis of graph forms shift operators that you have heard a bit from Luana yesterday, and in particular, it gives rise to finite range objects such as the shift operators of graph forms being Hilbert-Smith. And so these have particular consequences in machine learning, and that's where my focus, my research is focused on. So just from sample papers in 2023, we gave a transferability result. So you've seen a couple of transferability results. It's basically continuity proof of GNNs, deep learning architectures that has graph input. And we do this for about a degree graph sequences, which is as sparse as you can without making it disconnected. And I'm going to share a bit more about that because I personally think it's a nice piece of math that has only been introduced like a few years ago. So it may be of independent interest to people here. And for example, last year Luana and Stephanie wrote a paper that proved a point cache inequality for graph forms. So generalizing signal sampling in the style of Shannon-Nyquist theorems, but for graph forms. So identifying when you can have reconstructions of graph form signals, even like a subset of the signal space. Okay, so some food for thought. I'm interested in graph limits, and a lot of people are interested in graph limits from very different reasons. my direction comes from transferability, so I wanted to understand continuity of graph neural networks, different kind of graph neural networks, when the graph grows in size. This is a nice kind of overviews of different graph limits. Graph fonts is here. Then earlier in the day, you've heard about local convergence or local global limits, which is over here. And voila, there's a lot more notions of graph limits. Some generalize others, some intersect with others. And the sort of like largest kind of graph limits that generalize everything is called P operators. And I'll spend the next few minutes arguing that this is actually, the P operators actually quite amenable to deep learning analysis. And that's come from, originally, a graph of P operators are introduced by Backhouse and Shahidi in 2022, very recently. And we use this in our paper in newspaper in 2023. Backhouse and Shahidi comes from 2022. So let me describe to you how to lift a graph onto the space of probability distribution. And what I'm going to first describe is something called a one profile of a graph. So A here is the adjacency operator of the graph. For example, you have this graph, you have the adjacency operators. Now you take an arbitrary vector that is of R to the n, where n is the size of the graph. Then you apply the adjacency matrix, you have another vector. And this gives you a sum of Diracs over the space of R2. So I start from a graph that can have arbitrary size, n, and I end up with a distribution, Dirac distributions over a space of R2. And okay, so you may want to ask, okay, which vector should I use? And I say all of them. So if you have all of them, I have a set of distributions over R2. And that's define one profile of my graph. So this allows you to map, if you have a larger graph, the one profile is also a set of distributions over R2. Okay, so why stop at one initial vectors? You can do k of them. And it will be a set of distributions over R to the k, sorry, R to the 2k. And you can take, so you have two sets of distributions. You can take, for example, the Hausdorff measure between them. And solve the limit. This limit is defined, is metricizes by something called action convergence matrix, which makes sure that all of the Hausdorff measures between the sets decreases with rate that is, let's say, sub-exponential. So the nice thing about this theory is that this is essentially a limit of operators. A can be a nonlinear operator. You can think of it as not just the graph adjacency, but the graph adjacency composed with your nonlinear functions, which allows you to do more analysis than just point-wise nonlinearities in your networks. We haven't really tried it, but that's something that I would love to discuss if there's anyone interested. Okay, so that's first food for thought. And the second food for thought, probably for the more empirically minded person in the audience, is about metric problems. So assigning metric onto the space of graph is an age-old problems. We have things like graph fonts and cut metrics. We have graph hop and whatever the complicated metrics that I just described. Those are nice, but it's also too general. I think earlier there is some comments from the audience that graph limits are actually too strong for our purpose of transferability or understanding GNN. I agree. The power of graph limit comes from the fact that you can compare graphs of different sizes. So there you don't really need to worry about its power to do like isomorphic tests, for example. But again, computing cut norm, for example, is hard. Approximating is hard. So these are quite strong. What about metric with other computable graph machine learning architectures? Let's say I have an MPNN, which is one WL, and I have random weights. this gives you a pseudo matrix over the graph, over the space of graphs. It may, it may be nice in some way, not nice in others. But the questions that we want to ask, for example, for transferability, is the target functions Lifshitz, for example, nice or regular in some sense with respect to whatever MPN answer you have. You can also go to KWLs, or the more unknown version is what happens when you use a trained MPNNs. So this also ties back to Yusin's previous talk on how do you assume that there is a alignment between your task and your networks. So presumably a trained MPNN that works quite well on some tasks would have the perfect alignment trained. I mean, that's a hope, that's a dream. If we want to prove that you can actually, whatever we are doing in practice is actually working. And why stop at MPNNs? You can do more wilder stuff, graph transformers, LMs with graph inputs. What do you get in the end as a matrix over graph? Is this useful? Is this not useful? What can you say about it? And in light of Tim's previous talk, you can also think of this in terms of homomorphisms. These metrics, for example, cannot distinguish graphs, let's say that is of the tree with like 1, right? And so you can further ask, if I give you a homomorphism, let's say distinguishing closed families, can you, and that is computable. So there was some results about computability, complexity theory in Tim's talk. What kind of meaningful task can we make sure that the kind of metric that we have that aligns with that task? So if I give you a task, can you give me, let's say, a bunch of minors, and if I avoid these minors, then the task is Lifshitz or regular with respect to the metric. And so that's some random food for thought. If you're interested to discuss, I'll be happy to discuss. And that's all.
What did you mean by task is regular?
Right. So for like most generalization bounds, you assume that the target functions are kind of Lifshitz or have some kind of regularity, and then you have your generalization bounds. You show that it generalizes if you have that many samples, for example. So yes.
I'd like to thank all the speakers. First talk is 9. Boot camp starts 9 a.m. tomorrow. Be there.